Hello, everyone. My name is Jiayi Zhang. Call me Iris as well. I'm an undergraduate student from the University of Toronto. And today I'm going to present my work, Fast Updates for Least Squares Rotational Alignment, which is going to appear at Eurographics'2021. This is a joint work with Professor Alec Jacobson and Professor Mark Alexa. So let's take a look how it works together. Finding the best rigid alignment between two sets of corresponding points is an important computational problem across essentially all areas of science and engineering. Specifically, rigid alignment has become a time-critical task in geometric modeling and animation of elastic materials. In both cases, the behavior of a material is described by nonlinear energies that measures only the elastic deformation, but are invariant to local rigid motions. Problem statement of rigid alignment is actually extremely simple. Given two sets of points x and y, the essential goal is to compute the rigid transformation that minimizes the possibly weighted sum of square differences between corresponding points. Since the optimal translation is independent of the rotation and aligns the weighted centroids of the points, it's common to assume that the point sets have been translated so that their weighted centroids are in the origin and focus only on the more difficult problem of computing the rotation R. In other words, we constrain the matrix to live on the SO3 manifold. With elementary transformations, the minimization problem can be expressed in terms of the matrix trace, where the information about the relative orientation of the points can be compactly captured in the cross-covariance matrix M. This is a simple yet important problem, and people have been working on this for decades. As one of the building blocks in computer graphics, vision, robotics, and simulation, many applications rely on determining the 3D rotations, including camera alignment, ICP registration, as rigid as possible surface modeling, as well as rotational linear elasticity. It has been introduced under various names throughout the years, and a variety of solutions have appeared independently in the different fields. And the paper from Schoenemann at 1966 was credited with being the first one to solve the case of finding an orthogonal matrix using singular value decomposition and name it as the famous orthogonal Procrustes problem. To give a quick recap about SVD, it is commonly used vectorization of real or complex matrices. For example, we factorize M into the form U times sigma times V, where sigma is a diagonal matrix with non-negative real numbers on the diagonal, while both U and V are orthogonal matrices. Based on our survey of the literature, the SVD-based approach is also the one mostly commonly used in graphics. This explains the numerous effort in optimizing the computation of the SVD for 3x3 matrices on current multi-core hardware. Safakis et al. Have analyzed the operations necessary for computing the SVD of a 3x3 matrix and further exploits current hardware using SIMD and streaming architectures using SSE and AVX. To our knowledge, their code is the fastest popular code to compute the singular value decomposition. However, we observe that this is by no means the most efficient way to determine the rotation matrix, since to reconstruct the rotation matrix, it's unnecessary to also compute the diagonal matrix sigma, so some computational efforts will certainly be wasted, and you actually only need to compute the two orthogonal matrices and multiply them together. Instead, we formulate the problem of finding the rotation matrix into an optimization problem and start with reducing the degrees of freedom. Similar to lots of other parameterization of rotation like Euler angle, axis angle, and many others, we use Cayley parameterization based on skew symmetric matrices, where the small z is represented as unknowns. And then any rotation matrix, except for rotations by pi, can be expressed as follows. Let's recall our objective as stated at the very beginning. With the Cayley parameterization in hand, we can first do the change of variable and kill the explicit orthogonal constraint, since now any rotation matrix other than pi is captured by this parameterization. With further simplifications, in order to find the optimal rotational alignment, we now must determine the three variables that maximize this function. Unless the function is flat, and if a good starting point is provided, iterative maximization using the gradient is the method of choice. And in the following, we first discuss the standard Newton approach, and then explain how to improve by exploiting the quadratic rational representation of G. So first, we introduce the notion of manifold version of Newton's method. Given a point on the SO3 manifold, we're trying to avoid fitting a local tangent space and compute the incremental step in that space. The drawback is that in this case, we usually have to somehow determine the step size and reproject P back onto the manifold. So again, with this local parameterization, what we want to do is to construct a continuous invertible and differentiable mapping between a neighborhood of R on that manifold and an open set in R3. And then compute the proper update in R3 directly. Following that, after each time step, we multiply the rotation matrix with M, and then, in other words, reparameterize the rotation as origin and repeat this process until convergence. The extra benefit by doing this beyond a lower point on the error surface is to enable fast computation. Although it looks somewhat complicated, the function G is essentially a rational polynomial of Z whose derivative is very possible to take. And in our derivation, we also say that the derivatives are significantly simpler as origin, which is very nice. In our setup, the idea of reparameterization after the update leads to the following procedure. Start with any guess for the optimal rotation R0. This could be identity. However, we will explain later where this guess could come from depending on the application, which we call warm start. And in each step, apply the rotation, and then compute the optimal value and turn that into a rotation matrix R, and go back to the step 2 and repeat this process until convergence. Notice that a similar idea using exponential map has been presented in Kogelstadt et al., different by the way it is parameterized. We are going to show how the convergence could be greatly improved beyond standard Newton. So as we know, a common problem with the standard Newton approach is that convergence heavily depends on how well the function is locally approximated by the quadratic function derived from the gradient and the Hessian. And to ensure the desired definiteness of the Hessian, and thus the desired concavity of the local approximation around the maximum, it's customary to subtract a small multiple of the identity, while the proper constant value lambda is not trivial to determine. Rather than relying on such heuristics, it turns out that it's possible to characterize the maximum of function G in a helpful way. And our approach is inspired by finding an extreme points of a rational quadratic function, like given an extreme value of the function, which we call C, and we can turn the problem of finding the corresponding extreme point into finding a root of a quadratic polynomial. Following this idea, we first let G equals to C, which results in a quadratic equation in Z, and we have already known it has a single solution. And this reminds us that the optimal solution could also be characterized by setting the gradient to be 0. And notice that how this compares to the Hessian at origin. So to further interpolate this, when the optimal solution becomes to 0, namely C is equals to the trace of M, the above expression is just identical to the regular Newton step. And this really motivates us to modify the Newton step instead of blindly adding a constant, is to approximate the maximum value of G. To this end, we first split the M matrix into the symmetric and antisymmetric parts, and correspondingly split the G function into G symmetric and G antisymmetric, whose sum is always G. And we analyze their maximum values individually. For the complete details regarding the derivation, we encourage you to look at our paper, specifically section 3 and section 4. Finally, approximating the maximal value of C boils down to evaluating this expression. The simplest solution is to just take C as a trace of M, while a slightly more conservative approximation is to evaluate the L2 norm of M. However, the most accurate approximation requires to determine the largest eigenvalue lambda 2 of M, and here we use Gershgoring disk, and again we refer to the paper for the step-by-step derivation. So this plot basically shows the improvement of convergence with progressively better approximation to the maximum value in a single step. Notice that standard Newton step works well if the optimal rotation is small, but may fail to improve for larger rotations, while adding a small identity causes reduce the convergence speed for small angles. And our approximation based on the norm of M works well in both regimes. So all in all, based on the value of C, we propose a family of Cayley-based methods for which we name as Cayley, Cayley conservative, and Cayley Gershgoring respectively. And then we show how this could benefit the applications involving determining 3D rotations in different dimensions. So as we claimed earlier, to make the efficient computation possible, first we use Cramer's rule to solve the 3x3 linear system. And it is as cheap as only computing 4 determinants, each of which is composed of 14 multiplications, 4 additions, and 1 subtraction. Since many applications require best fit rotations for many, for example, millions of cross-covariance matrices together, we further optimize our code using single-core SIMD vectorization. We also rearrange input data layout for fast access. In the end, as lots of interactive deformation techniques, such as ARAP, involve solving many consecutive small updates, our modified Newton step could typically converge in one single iteration, which makes it possible to be even ultra fast. So with all of this together, here we demonstrate some of our results. Notice that the actual performance of different algorithms depend on lots of factors. For example, the specific implementation, the hardware, and also the data. In this case, another core contribution of our work is a comprehensive comparison among many, if not all, current methods for computing least squares alignment in one single framework, such that the users could pick the best suitable one for their specific input data. And we have already open sourced our code and put the link here. In order to provide meaningful statistics, we also collect a large number of data points from real applications as it will be more representative to benchmark the performance than randomly generated covariance matrices from a practical point of view. In terms of the accuracy, here we show that Cayley conservative generate much less failure cases compared to the naive Cayley, while Cayley-Gershgoring doesn't have any failure case at all, which confirms that more accurate approximation results in better convergence. But also notice that for a local global solver like ARAP, perfect convergence at each local step is not strictly required, since as long as the energy is reduced in each step, it will converge to a local minimum anyway. As for the efficiency, using SVD computed with eigen as a baseline, we compare the relative speedups of various methods. Notice that the perfectly converged Cayley-Gershgoring converges in 3 iterations on average and by 2.7 times faster. And this is already faster than all the other methods tested. Many applications in graphics also benefit from the high performance AVX vectorized code from Safakis et al. Treating this method as a baseline, the family of Cayley-based methods still achieves superior speedups, and even up to 70 times compared to the basic eigen implementation. It's also worth mentioning that typical implementations of the local global solver are bottlenecked by the least squares rotation fitting despite the sparse bank substitution theoretically having larger computational complexity. With our fast update, this is no longer the case, and the local step is an order of magnitude faster than the global step. To summarize, we introduced a family of Cayley-based approaches that enables fast computation of least squares rotational alignment problems. And there is no SVD efficient and also show better convergence by exploiting the maximum value of the function G. And we also provide our fast code and the implementation of all the other methods that can foster continuing development of rigid alignment algorithms. In the end, we thank all of our sponsors, as well as my co-authors. Thank you all for your attention.